Good morning, students. Today, we begin an exciting journey into the fascinating world of forces and motion. Every object around us moves because of stop motion, forces change speed, or even change direction. From a simple push on a ball to the launch at how forces affect motion. Let's explore the science that moves our world.
What you will learn in this chapter. Building on Chapter 4, where you learnt to describe motion using position, velocity, and acceleration, this chapter reveals why objects move, the cause behind every start, stop, speed up, slow down, and turn. You will meet the idea of force and master Newton's 3 laws of motion. By the end, you will be able to identify different forces and their directions, combine forces into a single net force, tell balanced from unbalanced forces, understand friction and how to measure it, state and apply Newton's first, second, and third laws. Use F equals ma to solve problems, and analyze forces acting on a system of connected objects. Everything from a kicked ball to a rocket's soft moon landing is hidden in these pages. Let's begin. The central question. Whenever something speeds up, slows down, or turns, ask yourself, what made that happen? Nothing changes its motion on its own. There is always a cause behind it, and by the end of this chapter, you'll be able to name that cause every single time. Do all motions need a cause? Here's a tricky one. If a ball is already rolling, does it need a constant push to keep rolling? Most people say yes, but we're going to test that idea carefully. Keep an open mind. The answer may surprise you. What this chapter covers. Our whole journey rests on 3 simple but powerful rules given by Isaac Newton. Master these 3 laws and you can explain almost everything you see moving around you, from a kicked football to a rocket going to the moon. Think it over. The canoe. Picture a boatman rowing. He pushes the water backward, yet the canoe goes forward. Strange, isn't it? And if he pushes harder, or if the boat is lighter, it shoots ahead faster. Hold these questions in your mind. By the end of the chapter, every one of them will make perfect sense. Force can start motion. A football lying still on the ground won't move by itself, will it? It needs a kick, a push. That push is what we call a force. So the very first job of a force is to wake up a resting object and set it moving. Force can change speed. Now think of a cycle you're already riding. Pedal harder and you speed up. Press the brakes and you slow down. In both cases, a force changed how fast you were going. So a force doesn't only start motion, it can also make things faster or slower. Force can change direction. Watch a batsman face a ball. The ball comes straight, the bat taps it, and off it flies to the side. The ball's direction changed because of the force from the bat, so force can also turn a moving object onto a new path. Force can change shape. Squeeze a rubber ball, press some clay, or stretch a rubber band. Each changes shape. That means force isn't only about motion. It can also squash, stretch, or bend things. Example, kicking a ball. This is our clearest example of force starting motion. The ball was happily at rest. Your foot supplied the force and it flew off. No kick, no motion. Simple as that. Example, striking a ball. In cricket, the ball is already speeding toward the batsman. The bat's force sends it in a completely new direction, maybe for a boundary. Notice, the ball was already moving, so here the force changed its direction. Example, squeezing a lemon. When your mother squeezes a lemon into the doll, her fingers press hard and the lemon changes shape and gives out juice. The lemon didn't move anywhere, the force simply changed its shape. Force has direction, friction. Notice something important. Whenever we talk about a force, we also say which way it points. Friction, for example, always pushes against the way you're moving, like an invisible hand pulling you back. Force has direction, magnetism. Play with 2 magnets and you'll feel it. Same poles push apart, opposite poles snap together. That push and pull is the magnetic force, and again, it has a clear direction. Force has direction. Electrostatics. Rub a balloon on your hair and it sticks to the wall. That's the electric force. Just like magnets, like charges repel and unlike charges attract. Direction again matters. Force has direction, gravity. Drop your pen and it falls down, never up. The Earth is pulling it with gravitational force, always toward the ground. That downward direction is why nothing floats away on its own. Force has direction, buoyancy. Push a ball underwater and feel it pushing back up against your hand. That upward push is the buoyant force. Water lifts things up, which is why a boat floats. Force is a vector. So here's the big idea. To fully describe a force, you must say how strong it is and which way it points. Saying 10 newtons alone is incomplete. 10 newtons toward the east is complete. Quantities like this are called vectors, just like velocity and acceleration. SI unit of force. Just as we measure length in meters, we measure force in newtons, written with a capital N. And here's a nice detail. Since it's named after a person, we write Newton in small letters, but its symbol N in capital. Note, changing a force changes its effect. Change how hard you push or which way you push, and the result changes too. A gentle nudge and a mighty shove do very different things, so both the strength and direction of a force matter. How do we measure force? We can feel a force, but feelings aren't science. So we ask, how do we put a number on it? How much force exactly? Let's find a proper tool for that. Spring balance and weight. You've all seen a spring balance in the lab. When you hang something on it, the spring stretches and shows the weight. And remember, weight itself is just the pull of the Earth's gravity on that object. Spring balance measures force in general. Here's a lovely trick. That same spring balance can measure any pull, not just weight. Hook it and pull the free end, and it tells you exactly how strong your pull is. It's our handy force meter. Threads of curiosity. Smallest felt force. Ever felt a mosquito land on your arm? That tiny touch is about 1,000th of a newton, a millinewton. That's roughly the gentlest force our skin can notice. Threads of curiosity. Tiniest measured force. And here's something astonishing. In advanced labs, scientists measure forces so tiny that our numbers need 24 zeros after the decimal. That's the octanewton. Science can sense pushes far beyond anything we could ever feel. Usually, many forces act. In textbooks, we often draw one neat arrow, but real life is messier. On almost every object, several forces act at once. Gravity, friction, your push, air resistance. So we must learn to combine them. Example, pushing a box. Imagine pushing a heavy box across the floor. You push forward, but the floor's friction quietly pushes back. Two forces, opposite directions, acting at the same time. That's the real situation. Example, ball floating on water. A ball floating on water is pulled down by gravity, but pushed up by the water. Two forces again, one down, one up. And because they match, the ball stays calmly floating. Tug of war. Think of the tug of war you play on sports day. Two teams, one rope, pulling opposite ways. It's the perfect picture of two forces fighting each other, and it will teach us a big lesson. Balanced forces defined. When both teams pull equally hard, the rope doesn't budge, right? These equal and opposite forces cancel out. We call them balanced forces. They're present, but their net effect is zero, unbalanced forces. Now, the moment one team pulls harder, the rope slides toward them. They win. The forces are no longer balanced. Motion happens only when one side wins the tug of war. Net force from unbalanced forces. The leftover, unbeaten part of the force is what we call the net force. Whenever forces don't fully cancel, there's a net force. And that net force is what actually changes the motion. Net force, opposite and unequal. When two forces oppose each other, just subtract the smaller from the bigger. The answer points in the direction of the stronger force, exactly like the winning tug-of-war team decides which way the rope goes. Net force, same direction. But if two friends push a stalled car together in the same direction, their forces add up. Teamwork. The net force is the total, pointing the way they both push. Example 6.1 setup. Let's put numbers to it. We have a block with a 10 Newton and a 6 Newton force acting in three different ways. Our job? Find the single net force in each case. Watch how the arrows decide everything. Example 6.1, Part A. Both forces pull the same way, so we simply add 10 plus 6 equals 16 newtons to the right. Same direction always means addition, like both friends pushing the car together. Example 6.1, Part B. Now they oppose. 10 newtons right, 6 newtons left. Subtract. 10 minus 6 equals 4 newtons, and it points right toward the bigger force. The 6 newtons simply eats into the 10 newtons. Example 6.1, Part C. Same numbers, but now the 10 newtons points left. So the net 4 newtons points left this time. See how direction, not just size, decides the answer? Always draw those arrows. Forces at an angle. So far our forces were in a straight line, but sometimes they pull at an angle to each other. Don't worry, combining those is a treat you'll enjoy in higher classes. Just know that it's possible. Turning forces. Ever opened a tap or turned a cycle's handlebar? You push one side up and the other down. Equal and opposite forces that make the thing rotate. That twisting effect is special, and you'll study it more later. Friction. Often overlooked, always present. Friction is the quiet hero, and sometimes villain, of physics. We rarely notice it, yet it's always there whenever two surfaces touch. Today, let's give this hidden force the attention it deserves. Why won't it move? Have you ever tried to push a heavy almirah and it just won't move, no matter how hard you try at first? Then suddenly, with an extra push, it slides. Why does that happen? Something is resisting you. Let's find out what. Friction opposes applied force. That resistance is friction, born where the object's bottom rubs against the floor. It always pushes opposite to your push, like a stubborn friend pulling the other way. When motion starts. So the almirah moves only when your push finally beats friction. The moment your force is bigger, a net force appears in the forward direction, and off it goes. Push harder than friction and you win. Other forces. Weight and normal. While you're busy pushing, two more forces are quietly at work. The earth pulling the object down, its weight, and the floor pushing it up, the normal force. Let's not forget these silent players. Weight versus normal force. Weight pulls down, the floor pushes straight up, and these two are equal. That's why the object doesn't sink into the floor or fly up. They cancel each other beautifully. Air friction. Even air pushes back on moving things. That's why you feel breeze on a fast cycle. But for a slow box on the floor, air's push is so tiny we simply ignore it. Small enough to skip. Note: net force decides motion. Here's the golden rule to remember. No matter how many forces are acting, the object only cares about the net force, the final winner after all the adding and subtracting. That's what decides its motion. Pause and ponder. Weightlifter. Picture a weightlifter holding a barbell perfectly still above her head. Can you name the two forces on that barbell? And since it isn't moving, what does that tell you about whether they're balanced? Think before you peek at the answer. Pause and ponder. Arm wrestling. In arm wrestling, when one player's hand starts tilting toward the table, what does that motion tell you? Right. The forces are unbalanced, and the winner is the one pushing harder. Motion always reveals the stronger side.
Moving objects stop. Stop pedaling your cycle, and it slowly comes to a halt. Stop pushing a ball, and it too stops after a while. Why? Because friction quietly keeps working even after you stop. Force needed against friction. So on a real floor, you have to keep pushing just to keep something moving. Not because motion needs force, but because you're constantly fighting friction. The moment you stop, friction wins and the object rests. Friction depends on surfaces. Remember from earlier grades, friction changes with the surface. A ball rolls far on smooth marble, but stops quickly on rough sand. The rougher the surface is, the stronger the friction. What if friction vanished? Close your eyes and imagine friction suddenly disappearing. You couldn't walk, cars couldn't stop, pens would slide off tables forever. It's a fun thought, and it shows just how much we secretly depend on friction. Materials. Let's do an experiment together. Collect 4 10-rupee coins, a strong rubber band, some tape, and a few flat surfaces. A wooden table, a laminated top, and a marble or tiled floor. Simple things from around you. Prepare the coins. Stack the coins neatly and wrap tape around the sides so they stay as one solid block. This little coin stack will be our traveling object. Mark A, B, C. Hold the rubber band stretched between your fingers on the wooden top. Mark its two ends, A and B, and a third point, C. That's how far back we'll stretch it each time. Marking carefully keeps our experiment fair. Launch and measure. Pull the coin stack back to C using the rubber band like a catapult, then release. Watch it slide and slowly stop. Measure how far it traveled and repeat 2 or 3 times so your result is reliable. Try laminated top. Now do the exact same thing on the smoother laminated top. Same stretch, same marks. Notice something? The coins glide farther and slow down more gently. Smoother surface, less friction. Try marble or tile. Finally, try polished marble. Even farther, even smoother stopping. Can you draw the conclusion yourself? The smoother the surface, the smaller the friction, and the longer the coins travel. You just discovered a law of physics.
Students, before we understand motion, we must first understand the idea of force. A force is simply push or a pull that can act on an object. When I kick at this football, I apply a force of more to pivot force for countless actions we observe every day. Every change in motion begins with a force. Understanding force is the first step toward understanding physics.
Good morning, students. Today, we begin an exciting journey into the fascinating world of forces and motion. Every object around us moves because of stop motion, forces change speed, or even change direction. From a simple push on a ball to the launch at how forces affect motion. Let's explore the science that moves our world. Students, force is not just a number. Force also has a direction. This force has a magnitude of 10 newtons and acts towards the right. The size of the force tells us its strength, rate, effect. Enlarging the direction of a force changes the effect on the object. To completely describe a force, we must know both how strong it is and the direction in which it acts. Students, now that we understand force, let's learn how scientists measure its magnitude. A spring balance is a simple instrument used to measure spring stretches, and the scale shows the force it's acting on it. The SI unit of force is the Newton, represented by the symbol capital of the spring. Using a spring balance, scientists can accurately measure the strength of a force. Students, forces often act together. Let's discover what happens when multiple forces act on the same object. When equal forces act they balance each other. Because the net is zero, the rope does not move. Now the forces are unbalanced. A non-zero in forces acts unchanged, while unbalanced forces cause objects to accelerate. Students, have you ever tried pushing something and noticed that it doesn't move immediately? This happens because a hidden force called friction acts against motion. When the applied force becomes greater or pitched than friction, a net force is produced and eventually the object starts moving. Without friction, controlling movement would be almost impossible. It is one of the most important forces in everyday life. Students, when several forces act on an object, we combine them to find the net force. When forces act in the same direction, we simply add their magnitudes. Combined effect of all forces acting to is called the net force. To understand forces more than an opposite threat. To understand motion, we must always identify the net force acting on an object. Students, have you ever tried pushing something and noticed that it doesn't move immediately? This happens because a hidden force called friction acts against motion. When the applied force becomes greater than friction, a net force is produced and the object friction is everywhere. In closed movement would usually be almost impossible. It is one of the most important forces in everyday life. Students, let's perform a simple experiment to discover how friction affects motion. The stretched rubber band applies a force that will launch the coins there forward. Notice how the coin down slowed after moving. The smoother the surface creates the smaller amounts of friction and the farther the coins can travel. This experiment clearly shows that friction controls how far an object can move.
Welcome aboard the Grade 9 Learning Mission. Every chapter becomes easy when learning is visual, exciting, and interactive. Watch until the end to understand every textbook concept clearly. Like, comment, and subscribe for daily learning. Visit rehanstudio.com for new CBSE practice questions and complete exam preparation.
Class 9 and 10 students, don't worry, make science and social science easy with your CBSE teacher. Subscribe now, like, comment, and press the bell.